I can start now, or okay. So hello everyone. So I think I can see some of you are here. So this is the second live session of the course Dynamic Behaviour of Materials. So I have not got many queries, I think, in the discussion forum or for this discussion, but I have some other queries where in the previous queries, some of the previous queries, so I can check and discuss on that. So if you have queries on this part of the course, you can post it on discussion forum. And I think our last live session, the third one, will be on I think 6th or 7th of October, just like 15 days from now. So all of you know that we have discussed earlier also, we are following only one textbook, the Mark Mears book, and there are some other maybe materials that is there not from that book, but it is very less. So mostly majorly we have one textbook only. So now I had some other queries earlier we got. So I want to just tell you briefly. So the one query was, if a pulse is transmitted into a material that has an amplitude exceeding the elastic limit, so this pulse will decompose into elastic and plastic wave. So why will the wave will decompose into elastic and plastic wave? So that is one query, like why it will decompose into elastic and plastic wave when the amplitude exceeds the elastic limit. So it's basically, while we can think it this way. So while the elastic pulse travels, the permanent deformation may not start at the time. But but the plastic waves, which means the disturbances in the form of permanent deformation, will depend on the strain hardening, the slope of the plastic part of the stress strain curve. So so basically, you need to think in terms of the even stress strain curve. So I think so slope of the plastic part of the stress strain curve will be different than the elastic portion. So but some materials, let's say for some polymeric materials, plastic waves may not be even present. So so when the amplitude is less, it will be elastic wave, and permanent deformation may not start. So when it exceeds the elastic limit, the amplitude exceeds the elastic limit, that means the disturbances are more, which can create permanent deformation. But that depend on that how much strain hardening is there, what is the slope of the plastic part of the stress strain curve. So yeah, there is another question on Shockwave, so which is interesting, that if we somehow prevents the release wave, that means the reflected wave, from entering into the target material, so will the shock wave will continue forever and will never dissipate? I mean, I understand it will be difficult for you to imagine this case. So what will happen is, we always say that we have a shock wave going, and then there's a release wave, which is also which will enter the target. So there can be a way, probably that may be ideal case, that we can prevent the release wave to enter into the target. So in that case, probably it looks like that the shock wave should never be dissipated. But I think in real case, there will be surely interaction with waves reflected from the other boundaries. So when you have a shock wave, even without, in absence of a release wave, still there will be reflection from the boundaries inside the target itself. So that will, I think, anyways, will the shock help to dissipate, the wave, the main wave. So yeah, so I think. Yeah, there is another interesting question I had got earlier. It is not in the discussion forum. So does the equation of state valid for metals? So equation of state, I hope all of you have studied. The equation of state, the question is, does the equation of state only valid for metals? And can it be applied to composites? Like composite means maybe some anisotropic kind of materials. Composite means fiber reinforced composite or concrete or whatever, that kind of materials. So the answer is, the most commonly accepted equation of state, or in short, we call EOS, equation of state. That is the most commonly accepted is the relation between shock wave velocity and particle velocity. We write U subscript S for shock wave velocity and U subscript E for particle velocity. So this relation is accepted as a linear relation for metals, and even sometimes accepted linear for other materials like polymers and composites. Sometimes it is, metals for sure, you can assume it to be linear relation. But even for polymers and composite also, it is sometimes accepted as linear relation. However, if it is an anisotropic material, anisotropic material means it depends. When you call isotropic and anisotropic, I think I have discussed this in even in the materials science basic part as well. So when you call anisotropic and isotropic, you need to be very careful, because let's say for a crystalline material, for polycrystal, we call it as an isotropic material. For single crystal, we call it an anisotropic material. So even for other materials also, we need to be a little careful. Suppose for the same metal, roll sheet can be anisotropic, right? So that I think you have seen. So whether a material is anisotropic or isotropic, that will be, it may not be purely isotropic or purely anisotropic, but we may assume it. Sometimes the polycrystalline materials may have some anisotropic character, but we assume it to be isotropic. I hope that was discussed in that, you have probably understood it from the materials basics chapter. And so sorry, I just got deviated from this. The question was whether the equation of state is valid for only metals, and whether it is valid for other composite kind of materials as well. So the answer is yes, for metal it is linear relation, and also for some materials like polymers and composites, which may not be always isotropic, for those materials, so sometimes we use linear relations. But however, for generally anisotropic materials, that means if you are sure that materials is purely anisotropic, you can call it. It is generally anisotropic, we call. Anisotropic means there are other, there are different variants of anisotropy. I will tell you just after this. So if it is an anisotropic material, so the equation of state may have nonlinear relationship that with higher order terms in the equation. What is the equation of state? That is so that equation of state relation can have more terms with higher order. That means that is a non-linear, not like a a simple linear relationship, whatever we have discussed in our class. So we are not going to discuss on the non-linear one, but you should understand that there can be more complex equations which are non-linear. We are talking about equation of state. So you can probably, if you are interested, you can search on internet about equation of state for composite materials or equation of state for concrete. I'm sure there will be published literature, especially research papers, where they have discussed on that. So now coming to this anisotropic again, what is anisotropy and what is isotropy? When you call anisotropy, there can be different variant of it. I mean, some of you probably know that. Even we call some materials as orthotropic, some materials as transversely isotropic. Some of you have probably studied some courses on composite material, then you will know. And there are other kind of anisotropy, like for single crystal material, if it is single crystalline material, but only one grain, one crystal. So that crystal can be different, crystal systems, right? It can be cubic, it can be orthorhombic, it can be tetragonal, it can be hexagonal or monoclinic, triclinic. So those kind of different crystal systems, may have different kind of anisotropy. If you only talk about one single crystal, only one grain. If you have a polycrystal where you have thousands of grains, or even more than thousands, millions of grains, then the crystals can be assumed as isotropic. Why? Because they have randomly oriented grains. We average out the properties. But now coming to one grain problem, like if it is a single crystal, sometimes people make a big single crystal for turbine blades. Some nickel alloy, let's say nickel super alloy, they make single crystals. Let's say the metallurgists are so expert now that they can make a big single crystal. Otherwise, the crystal is very small in the micron level, or sometimes it can be in a nano level. Now it is they engineer nano crystals as well. So now my point is, if you take a single crystal, if you are expert enough to get a big, let's say single crystal, and that single crystal, if it is a cubic material, FCC, BCC, then it may have, that is a cubic symmetry it has, and the number of elastic constants required to express stress strain relations will be only 3. For isotropic, it is 2, elastic constants, which is like it is like it is not exactly elastic constants. It may not be exactly Young's modulus and Poisson's ratio, but the expression containing Young's modulus and Poisson's ratio. So there are two. I'm not going to details of it. Some of you already know that when you have a stress tensor and strain tensor, the relation between the stress and strain have some components, stiffness components. So now what I'm saying is that if it is a cubic material, you need 3 elastic constants. If it is a purely isotropic material, you need 2 elastic constants, 2 independent elastic constants. And then if you have a material which is orthorhombic or tetragonal, you need different, maybe for tetragonal, let's say you may need 6 or 7 elastic constant. Orthorhombic is similar to orthotropic in, our composite case. Orthotropic composites and orthorhombic single crystals they are similar. So similar symmetry, material property symmetry, and that will give you 9 independent elastic constants. For monoclinic, you need to have 13 independent elastic constants. So what I'm saying is that for different crystal structures, if you want to take only single crystal material, then the number of elastic constants will be different. It can be 3, it can be 4, or it can be 6, it can be 9, 13, or something like that. If it is a purely anisotropic material, we call purely anisotropic. That means it has the highest level of anisotropy. There is no symmetry at all in the arrangements. So then you need 21 independent elastic constants to express the stress strain relationship, the generalized Hooke's law. So that's why when you call my point is why I am explaining all these things. When you say anisotropic, or anisotropic material, there can be different kinds of anisotropic. So we need to be a little careful on that. So that I think a little bit advanced. We have not discussed much of it, but this is very important for a mechanical behavior of material, and especially for, let's say, composite materials. Some of the composite materials um, we assume it to be orthotropic material, where you have three planes of symmetry. So please check that if you are interested to know the three planes of symmetry, like mirror symmetry or reflectional symmetry. So, and there is another composite we call the transversely isotropic material. So there you have only one axis of symmetry, or we call one plane of isotropic. So then you need five elastic constants to represent stress strain relationship. For orthotropic, it is 9 independent elastic constant. For transversely isotropic, it is 5 independent elastic constant. And if it is purely anisotropic, or we call it actually generally anisotropic, then you need 21 independent elastic constant. Basically, when you have more number of elastic constants or more number of independent elastic constants are required, then the material has lesser symmetry. If it is less, then it has higher, less number of elastic constants are required. Then it has higher symmetry. So that is one thing. So as you know, that isotropic cases, if it is an amorphous material, or if it is a polycrystalline materials where we have randomly oriented grains, then we call that the isotropic, or we at least assume it to be isotropic. The properties are the same in all directions. And another query was earlier I have found that the graphical solution, the method we have used is we call impedance matching technique. There's a method called impedance matching technique. I hope you have found that. So generally in that we equate the pressures, and the query was why the impedance matching technique was why the technique is called impedance matching technique, when actually we are equating the pressures, we are matching the pressures, not the impedance. So why it is called the impedance matching technique? That's a good question. So basically how the pressure varies depends on the impedances of the material, and hence it is named as impedance matching technique. That basically we're matching or equating the pressures only. That is one query, and another query was Shockwave is defined as the continuity of pressure, temperature, and density. Shockwave is defined as discontinuity of pressure, temperature, and density. Yes, if the variation of only one parameter happen and the other don't vary appreciably, will it be called shockwave? So there are pressure, temperature, and density. Discontinuity is there in shockwave. So the question is, if the variation of only one parameter happens, the other two don't vary appreciably, will it be called shockwave? Yeah, the answer is basically, when we call shockwave, it is generally shockwave is known to be generated due to high pressure. When you have high pressure involved in this, then shockwave can be produced. And if the shockwave shockwave is produced, it will surely produces discontinuity of not only pressure but then temperature and density will be there. So due to high pressure, actually it is on the shock front, so that discontinuity will be there. And there may be a question on and also high amplitude disturbances, when the amplitude of disturbance is high, then uh, that that then the wave travels faster. So that another query is why it happens. So when it is a high amplitude wave, isotropic, generally the waves are isotropic. The high amplitude wave, if it's I mean basically the disturbance, if it has the high amplitude, why it travels faster. So it happens generally for plastic waves, uh, elastic waves. We told that the amplitude is less. For plastic waves, even the shock waves is also kind of a plastic wave. So then what happens is, if you have higher amplitude, that results in higher wave velocity, because the maximum displacement of atoms from the equilibrium position is the generally we call amplitude. So you have atoms, and then atoms will vibrate like this. Even if you do not have a wave propagation, the atom generally vibrates, right? That's a very high frequency vibration. It's a 10 to the power 13 also. You have the frequency right there. So that when you have, you have a high amplitude wave, that means the atoms will vibrate more from the equilibrium position. So then, if you see, if you have higher uh, oscillation from the equilibrium position, it will surely, result in a higher velocity. It is if you imagine with some atoms, and that will be, I think, that will make it clear. So you draw some atoms and show the amplitude of the vibration. So then there was uh, there was another question, but I have half of it. May not be the entire question. The sound velocity will be more in a medium with a higher density. Uh, uh, okay, actually the question is like this. I have missed a part, I think, the one sentence. If the wave velocity varies with the local pressure, every sound wave will be a shock front. But this is not the case. Why wave velocity varies with local pressure? What is the um, okay? Sorry, I did not get the question. I mean, I had pasted it here in file. So that is, I think I need to check it again. It's not very clear to me now. Maybe I put half of the question here. Uh, so if there are any other questions, let me check. So I just want to tell you one more thing. I think I got another queries on this. Earlier I got these queries. This may not be in this forum. So what is the wavelength generally represents physically? So what happens is, the query was, what does the wavelength represents physically, and like if we have two different wavelengths of the spectrum, they represent different colors. How does the mechanical wave will differ from each other, having different wavelength in their behavior? Okay. So on what factor does the wavelength of the mechanical wave depends? So basically the answer is the distance between the centers of two consecutive compressed zones. So you have, when the wave propagates, like sound wave, right? There's a mechanical wave. So one compressed zone here, one compressed zone here. The center of these compressed zone and this compressed zone So we can call it the distance between that is we call the wavelength. So the visible light in the sound, in the audible sound range. Audible sound range means there is, as you know, right, like uh, not all the mechanical wave frequency, as you know, that elephant can hear some other sounds as well, right? We cannot hear, or maybe dogs can hear some other sounds. So there's a range of frequency, or you can call it a range of wavelength, where we have the audible sound like our visible light. Not all the electromagnetic radiations, so radiations also we can see with our eyes. So similar to the visible light, the audible sound range also. Um, if the change in source frequency happens, that will result in change in wavelength, and that will result in sounds of different pitches. So if your the source frequency, there is, let's say, some instrument somebody is playing, and if the frequency of that instrument it changes, then that will change the wavelength, the velocity of the sound. If it is let's say half a kilometer away, if there is some music function is going on, then probably for different instrument sounds, it will musical instrument sounds will come to you at the same time. The velocity may be in the same in air, velocity of sound, but then if the frequency is different, the wavelength can be different, and that results in sounds of different pitches. Pitch is different due to the different frequency. So that's how, like, for like visible light, right? You see different colors: blue, red, green. So similarly here, we get different pitches. So different frequency will result in different wavelengths, and that we can call that the pitches are different. Yeah, generally the sound source frequency will determine the wavelength. And also in the impact problem, like now we talked about the sound wave from a musical instrument. In impact problem, what happens is, as you know, even in Street Hopkinson pressure bar, so when you are impacting your bar, so how much initial displacement happens, so that will decide the wavelength. That we already have studied that, right? That a length of the striker bar will influence the wavelength, so that we have studied. So that will decide the wavelength. And also, wavelength will depend on the medium in which wave propagates. So if the medium is different, you take different material rods. The wavelength rod means, let's say we have different solid material and the long rods. So and we are you are actually, like, impacting with some striker, and then the wavelength generated in different materials, or different material and different rods made of different materials, so that will be different. So medium also influences the wavelength. Yeah, so I think yeah, that's all I think we have. And I think there is no queries now here. So if you do not have any query, probably uh, we can probably stop here today. I thought maybe you have some queries, but anyways, you can post in the discussion forum. My TAs will check, and teaching assistants, we have four of them, so they will help. They help me in getting these queries, or uploading assignments and all other work. So I think they will let me know about your queries, and I will answer accordingly. So if you do not have any queries, I think we can probably finish it today here. I think there is no more queries. No more queries means there was no query actually. And then yeah, I think we can stop now if there is no queries here. Okay, I think thank you. So there is no queries. Thank you. So we'll meet on again on I think on 6th October.